Okay, this screencast is covering slides 9 through 12 in the version of the PowerPoint dated January 28, 2016. The purpose is to dig into the nuts and bolts of the first law in thermodynamics, understand one of the different kinds of energy that underlies this law in both qualitatively and quantitatively, and to understand the intimate connection between the first law and the principle of conservation of energy. And so the first law can be stated in many different ways. The one common statement, and one that I like, is heat is work and work is heat. And again, one of the purposes of this presentation is to begin to understand more specifically and more deeply what that means. So another way to put it is that heat is work and work is heat, and both of these things are manifestations of what in classical mechanics or quantum mechanics would be considered energy. So that's a key concept here. Again, the first law of thermodynamics is intimately related to the principle of conservation of energy. You could expand the statement "heat is work is heat" and say heat is work is heat. In both of these, in all of these things are different manifestations of energy. Now when we go on to talk about sort of the technical aspects of solution thermodynamics, this form of energy is referred to as enthalpy. And so the reason one way to understand why we have a different term for what in classical or quantum mechanics is just called energy is that in thermodynamics we're going to, of course, talk extensively about free energy. That plays a very important role. We'll talk in detail later soon about what free energy is. And free energy we'll see is something really quite different from energy according to classical mechanics or quantum mechanics. So that kind of classical mechanical energy is going to be called enthalpy when we talk about solution thermodynamics. So then we could state the first law is heat is work, work is heat, and both of these things are equivalent to enthalpy, which is equivalent to what in classical and quantum physics is called energy. All right. And so, as I said before, a key point underlying the first law of thermodynamics is the principle of conservation of energy. Heat and enthalpy, heat and work are all conserved. And then the development that will be presented on the next slide is going to show you exactly how and why this works in one specific case. All right. So what is work? Well, the physicist's definition of work is that it's force times the distance over which it's applied. This is, formally speaking, it's a kind of path integral. To simplify that somewhat, it is simply the projection of a force vector along the direction in which it is applied. And so it is the integral, basically, of that projection of the force vector along the distance which the force is, along the direction in which the force is applied. And then, so just work is essentially force, the component of force along the distance of application times the distance along which it's applied. All right, so for illustrative purposes, we're going to simplify this, and rather than having a vectorial quantity, we're going to take a very simple but very important example, and we're going to assume we have a ball or particle at rest in our current frame of reference, and we're going to have a force pushing in some direction, and we're simply going to let the force we're going to let the ball or particle be accelerated by that force. So the force is pointing in this direction, and the ball will move in that direction. And so the force in this case is parallel to the direction of movement or application of the force. And so that gets rid of the dot product and simplifies it just a little bit mechanically. And so then what we want to do now is take this simple situation, this simple model system, and use the laws of Newtonian mechanics to figure out what kind of work is done in accelerating the particle to a given velocity. Right? If we take a particle at rest and apply a force, it will begin to speed up, it will be accelerated. As long as we continue to apply the force, it will continue to be accelerated. When we release the force, it will no longer be accelerated. And so what we want to do is calculate the net amount of work using this definition. We want to calculate the net amount of work done on this particle in the course of speeding it up or accelerating it to some final velocity v. And so mathematically, this is pretty simple. Again, we go back to Newton's laws. Force is mass times acceleration. Acceleration, of course, is the rate of change of velocity with time. And velocity, of course, is the rate of change of distance with time. So we can rearrange this relationship here, v equals dx dt, to give us dx equals v dt. All this says is that for a particle moving at some instant in time with a velocity v during a infinitesimal increment of time dt, the distance traveled by the particle is dx. And that just comes directly from effectively the mathematical definition or phrasing of velocity. All right, so now all we need to do is apply the physicist's definition of work to this acceleration process using Newton's laws. So we have the work done on the ball is the force. The dot product of the force with the direction in which it's applied. In our example, these are collinear. The dot product drops out. So we have force, which is mass times acceleration. As we have up here, mass times acceleration is mass dv dt. So mass times acceleration is mass dv dt. That's mass times acceleration dx. Right, so force is mass times acceleration. Just note that here, right? Force is mass times acceleration. So here we have the dot product of force over the distance of which it's applied, and so here we have mass times acceleration, which is force times the distance over which it's applied. And so that gives us, because again the force and the velocity are co-linear along the direction of motion, the dot product drops out, and we get simply the work done in accelerating the particle is mass times dv dt, the integral of mass dv dt dx. Okay, so this integral is relatively trivial to solve. We're just going to replace the dx here, which is the infinitesimal distance traveled over the infinitesimal of time dt. We replace dx, that infinitesimal displacement, with v dt. And then we get the integral of m dv dt v dt. And so this is a very simple thing to integrate. An integral is, of course, an antiderivative. If this integration is correct, we should, when we differentiate this, we should get this expression. And so by the simple rules of basic calculus, if we take the derivative of 1/2 mv squared, of course, m is constant with time, so that's a constant. We get the derivative of v squared is 2v dv dt. So 2 times 1/2 cancels out, and so we get mv, right? The derivative of v squared is 2v dv dt. So the 2 drops out, we get v dv dt. So we get m dv dt. I'm sorry, m dv dt v dt. All right, so this all works. And then what we want to do, if the particle started out at rest, its velocity would initially have been 0. And then if we accelerate to a final velocity of v final, this expression gives us that the work done in accelerating the particle is 1/2 mv final squared. Now, of course, this expression you've seen, I assume, many times before. This is what you've been told, and you may have seen this derivation at some point in the past, or it's possible you did not. But in any event, this is why the kinetic energy, this is where the term for kinetic energy comes from. It comes simply from applying this definition of work using the laws of Newtonian mechanics to figure out how much work is performed in accelerating a particle from rest to a final velocity v squared. The amount of work performed is 1/2 mv final squared. And so the kinetic energy stored, what you've always been told is the kinetic energy stored in this moving object is exactly equal to the work that was done in bringing it to that speed. Okay, so what do we learn from this? Well, again, I've heard probably many, many times that 1/2 mv squared is the kinetic energy. And what we've learned then is that the kinetic energy is the amount of work required to accelerate an object from rest to speed of v final. And therefore, the kinetic energy is the amount of work stored in a moving object. And it's also exactly equal to the amount of, sorry about that, it's also exactly equal to the amount of work that can be recovered from a moving object when it is decelerated to rest. So this is sort of another essentially corollary of Newton's laws. You've probably heard of this, something like this principle: to every action there is an equal and opposite reaction. You can only change the velocity of the ball by exerting a force on it. Exerting a force on it as it moves through space does work. The amount of work done in bringing it from rest to some final velocity is 1/2 mv squared. If you were to take this thing now and actually stop it, you would have to exert a force on it that would do exactly this amount of work to remove that amount of kinetic energy from it. So again, kinetic energy is the amount of work required to accelerate an object from rest to speed of v final. It is, of course, what we say is the energy stored in the object, and then that energy is conserved because to reduce the velocity, the particle would then have to do would be doing amount of work exactly equals the kinetic energy. So this relationship between work and energy is absolutely fundamental. It is essentially an explanation of why energy is conserved. There are different ways to look at it. You could look at it as an explanation of why energy is conserved. That would be one way to look at it. You could also look at it as just a manifestation of the principle of conservation of energy. But as we look forward now to thinking more deeply about what's going on in solutions and what's going on in the interaction between macromolecules, the key point here is that in a solution, the way this relates to a solution is that in a solution, particles are moving around. As they're moving around, of course, they have kinetic energy. That kinetic energy is exactly, they could only get to that, whatever velocity they're at some point, work was done on them, bringing them up to that velocity. If their velocity changes, the particle will have to do work on something else, and exactly the amount of work that it does will correspond to the amount of kinetic energy it loses, and exactly that amount of energy will go into something else. And we're going to think next about what were other places it could go. And so, again, there are a couple of purposes of going through this little exercise. The first is to make sure we're, sort of starting from a common and rigorous point in terms of understanding what energy is. And the second is to begin to think, again, about in biochemical systems exactly where energy is stored, exactly how energy moves around. Energy moves around because force is applied over some distance. A particle that has some kinetic energy can only lose it if it does work on something else and transfers exactly that amount of energy to the other thing. And so, effectively, this is what's going on all the time in solutions, one of the many things going on. And so this is a good starting point because the physics are relatively simple, but they're tremendously important, and they're nicely illustrative of the first law of thermodynamics: heat equals work equals enthalpy equals classical mechanical and quantum energy. It's also nicely illustrative of the principle of conservation of energy. And I think it's probably helpful if you now think about exactly how this relates to what happens when the urea crystals are put into water. And the process of dissolving the urea involves a reduction in the process of the water. One critical thing going on in that process is this kind of transaction between kinetic energy and other forms of energy that we're going to talk about shortly. So to summarize and finish up, this is one specific example of how heat equals work. In this case, heat equals work equals enthalpy. This form of enthalpy is called kinetic energy.